Okay, folks, it's good to be back with you today. We're going to continue on and finish up 9.2. Now, if you remember, the title of 9.2 is Multiplying and Dividing with Radicals. And then in each one of those operations, there is a simplifying part that we do as well. We have taken care of the multiplication. We're going to now finish up with division, and then that'll complete 9.2. Well, just like multiplication had a product rule of radicals, division has a quotient rule of radicals. And so we're going to go to the board and we're going to define this quotient rule of radicals, because it's the key property that we're going to have to use when we do the division. The quotient rule of radicals says this. Here's the premise statement. If A and B are real numbers where roots exist and B does not equal 0, here's the equation that defines the quotient rule of radicals. The nth root of A divided by the nth root of B is equal to the nth root of the quotient of A and B, or is equal to the nth root of the radicand A divided by B. Now, all you're looking at are variable expressions right there. But we want to prove this rule again, so we're not just asking you to accept it. Let's say the value of A is going to be 81. Let's say the value of B is going to be 9. Remember, A and B can be any numbers just as long as the roots exist, with only one restriction. The value of B cannot be 0, and the value of B is not 0. So let's plug the 81 and the 9 respectively into this equation. The square root of 81, my index is going to be 2 again. The square root of 81 divided by the square root of 9 is supposed to be equal to the square root of 81 divided by 9. Let's return to the left-hand side. If we go up to the numerator on the left-hand side and simplify the radical of 81, that's 9. And if we simplify the denominator radical, that is 3. If we go over to the right-hand side and we literally divide the 81 divided by the 9, this entire radicand right here, 81 divided by 9 leaves us with the radical of 9. Back to the left, 9 divided by 3 is 3. And the radical of 9 simplifies to 3. 3 equals 3. This must hold water. This must be true. And it is true. Now, just like the product rule had two different sides to it, one of them was to multiply and the other one was to simplify, so goes division. We're going to start down here with letter A, and we're going to divide with radicals first. And you'll notice what is written in the red box right here is the form that you'll see when an instruction is asking you to divide. Because after all, notice how we say this expression on the left. the nth root of a divided by. We're dividing. We're going to start out dividing with radicals. Divided by the nth root of b. So people, when you are asked to divide, you are going to be given this type of form. The form that speaks to division. The nth root of a divided by the nth root of b. So this is the form that's going to be given to us. And we're going to find out momentarily that in order to divide radicals, we're going to have to rewrite this expression in the form of its equivalent measure that we see on the right-hand side. And that's going to have to be done because in order to divide with radicals, we have to now introduce a new rule. Now, we've talked about 3 rules so far. I'm not going to summarize those now, but we've covered 3 rules pertaining to radicals. In order to divide with radicals, we need a rule number 4, and it is going to have to be memorized, and it will not take long, but it does take time. Here's rule 4. When dividing with radicals, the denominator cannot contain any radicals. Back over here first in the red box. When we are dividing with radicals, there can be no radical in the denominator. In other words, the value of the denominator can never, it cannot, number one, it can never be 0, but number 2, there can never be a radical in the denominator. That is a rule. It's an accepted rule. So we're going to begin with problem number 1. Notice the directions say divide and then simplify if necessary. So we look at number 1. The radical of 60 divided by the radical of 15. Number 1, in the red. It's in the red form. Now, the rule says when we're dividing, we cannot have a radical in the denominator. And there's no immediate way to get rid of that radical of 15 because 15 is not a perfect square. And it can't be simplified any further. So what we're going to have to do to divide the radical of 60 by the radical of 15, we're going to have to rewrite this expression. And we're going to have to rewrite it in the form that this red one is equal to. We're going to have to write it in the form of the radical of a divided by b. Or in other words, I'll put it right over here. We're going to have to write problem number 1 as the radical of 60 divided by 15. Because that's what the red one is equal to. We have to write it in this form. And we did. Now, let's check to see if we can simplify this radicand. 60 divided by 15. If you were to take that calculator and divide 60 by 15, it will divide evenly. It will go exactly 4 times. And so we'll get it down to this. The radical sign is still there, because all we're doing is dividing 60 by 15 right now, and that's 4. And now look at where we're at. We're down to the radical of 4, and now we're at rule 1. If the radical represents a rational, we write the rational. That represents a rational. Its rational is 2. Done. So we couldn't get anywhere with this one, leaving it in this form. We had to rewrite it. That's the quotient rule of radicals. There's number 1. Let's go to number 2. Make the division sign. And we'll go with a different index. The cubed root of 72x to the 8th divided by the cubed root of 3x squared. The direction? Divide. But we can't have a radical in the denominator. And the denominator cannot be simplified right now because our index is 3, and that's not a perfect cube. No part of it is. So we're going to have to rewrite this. We're going to have to rewrite it using the quotient rule of radicals. And so we make one radical sign, and we place that index of 3 in that cavity, and this division statement is equal to the cube root of 72x to the 8th divided by 3x to the 2nd. Now we look at the overall radicand. We're going to divide 72 by 3, and 72 will be divided by 3 evenly because 7 plus 2 is 9. And we most definitely can divide the x to the 8th by x squared because the bases are the same, so we'll subtract exponents. So let me just kind of elevate it right up here. (72) divided by 3. Well, if you divide it, it will go 24 times. And x to the 8th divided by x to the 2nd, if we subtract the exponents, we'll get x to the 6th. Now we've got it down to the cubed root of 24x to the 6th. And we want to simplify that if it's able to be simplified. Well, very definitely x to the 6th is already a perfect cube, because its exponent 6 is evenly divisible by the index of 3. 24 is not a perfect cube, but possibly within 24 there is one. Now, I'm going to come right down over here, and I'm going to write down that 24, and I'm going to prime factor it. Then we'll see if it's got a perfect cube factor. We can put a 2 into it. That'll be 12. We can do another 2, and that'll be 6. We can do a third 2, and that'll get it down to 3. And we have enough. So now we're going to take this cubed root of 24x to the 6th, and we're going to simplify it. We're going to bust this down into 2 separate radicals. Put that index of 3 in each one. This is going to be the rational house, and this is going to be the irrational house. Let's start with the rational. 24 factored to this. We had 3 factors of 2. I'm not going to multiply them together to generate 8 and put 8 there. I could, and you may. I'm going to leave it as a power. So we'll put the 2 cubed there. And the leftover 3, that's irrational. That will go in the irrational house. So now we've taken care of the 24. The x to the 6th, we've already made commentary on that. That's a perfect cube right away. So it doesn't have to be split. Put that x to the 6th right next to the 2 cubed. let's get this one out of its house, because this represents a rational number. 2 to the third. Its exponent matches the index. Bring down the 2. 3 divided by 3. 2 to the 1, or simply 2. Bring down the x. 6 divided by 3 will give us x squared, multiplied by the cubed root of 3. Wrap it up. Done. So we kind of jumped right into something that maybe had a little oregano in it. But it's right there. All right. Let's go to 3. Number 3. 48 multiplied by the square root of 50x cubed divided by 12 multiplied by the radical of 5x. So you see the presence of the fraction bar? That means divided by. That's red. That's the red form. What's different is we've got a factor of 48 here, there's an implied times sign here, and then we've got this radical factor. We've got a 12 as a factor, and we've got another radical factor of 5x. The first thing that we might want to do is this. Let's split this up pretty much right down the middle. And I'm going to write it like this first. 48 divided by 12 times the radical of 50x cubed divided by the radical of 5x. I'm able to do that. There's a times sign there, and there's a times sign there. So we can write this as a separate division statement, and we can write that one as a separate division. Now, we'll go ahead and divide this out because 48 divided by 12 goes exactly 4 times. So we'll bring down the 4. And now we're going to move into the quotient rule of radicals right away. I'm not going to recopy that format down again. You cannot have a radical in the denominator. We have one. So we're going to have to rewrite it in the green form. So 4 multiplied by the radical of 50x to the third divided by 5x. Now I'll elevate it right up here. Bring up that 4. 50 divided by 5 is 10. X cubed divided by x to the first, 3 minus 1, x squared. Now we're down to 4 times the radical of 10x squared. The x squared is a perfect square. Our index is 2. Nothing can be done with 10. Just pausing there for a second. If you prime factored 10, you'd have 2 times 5. You don't have 2 of a kind. So I'm going to use the product rule of radicals to split this up. Bring the 4 down. We'll make 2. The x to the second is a perfect square. It's going to go in house number 1. The 10 is irrational because it doesn't contain any perfect square factors. So we'll put the 10 in there. And now let's carefully bring down the 4. We're going to multiply it now by the radical of x squared, which is x to the 2 divided by 2, or x multiplied by the radical of 10, for x root 10, done. And we have it in simplified radical form. Now, one more last one for this portion of the video. And then we'll do a little pause. And this is the fourth of 4. Just so you have them there. One last one. 27 multiplied by the cubed root of 240 divided by 36 multiplied by the cubed root of 3. Similar to the last one. I've split it down the middle. 27 over 36 times the cubed root of 240 divided by the cubed root of 3. Now 27 over 36, that's a proper fraction. It's not a situation where we can divide. We have to reduce it because it's proper. Now, I could prime factor those numbers, but I'm not, because we should be able to look at the denominator and the numerator and see that 9 would be the greatest common factor of both of those. And if we divide 9 into both the numerator and the denominator, we'll get 3/4 times, and now we're going to split it and write it under one radical. Cubed root 240 divided by 3. Now let's elevate it up here. 3/4 multiplied by the cubed root of 240 divided by 3, which will give 80. And now we have to see if 80, that radicand, can be simplified, and if we are able to get a perfect cube factor out of 80. So let me just kind of erase this little part right here so we can clearly show that upside down division for 80. And then we'll see if we have enough. 240, 220, 210, 5. The index is 3. That means we need 3 of a kind of any of those primes, and we have 3 of a kind. So, 3/4 times. Now we'll split it using the product rule of radicals. Try to remember that index of 3. This is the rational house. This is the irrational house. Let's take care of this. Here's our 2 to the 3rd. That's rational. And the product of these 2 little leftovers right here, because there weren't enough of them, multiply them. That will be the radicand of the irrational. Bring down the 3/4 times the cubed root of 2 cubed. 3 divided by 3 is 1. It'll just simply be 2 multiplied by the cubed root of 10. Now, folks, that 2 that you see right there, we need to probably write it as a fraction because this 2 has got to be multiplied with that 3/4, and it would look better if we made it a fraction and wrote it over 1. We could then cross cancel, and we need to. 2 will divide into itself once, and 2 will divide into 4 twice, and we'll have 3/2 multiplied by the cubed root of 10, and we can put that little guy to bed. He's done. Okay. Now we've taken care of now dividing with radicals. Okay, we're going to resume with the final part of 9.2, staying with the operation of division. In the last segment, we use the quotient rule to divide. And this was the form right here, if I can just point to it. This was the form that the expression was written in when it called for us to divide. And what did we need to do? We needed to take this form and rewrite it in its equivalent form that's over on the right-hand side. Why did we have to do that? Because when we are dividing with radicals, no denominator can contain a radical. And there's a radical there. So we have to rewrite it. And when it's rewritten in this form, then we're not breaking that law. Well, now we're going to go the opposite way now. Now we're going to go the other way. Now we're going to use the quotient rule to simplify radicals. And now I guess we can say the shoe is on the other foot now. Now the form that we're going to be looking at and emphasizing is what you see in red right here. This is the form that the radical expression will be written in when we need to simplify. The nth root of the radical of a divided by b is equal to the nth root of a divided by the nth root of b. When we are simplifying radicals using the quotient rule, the problem is going to be written in this form. The problem is going to be written in this form. You see, here's your nth root of a divided by b. Here's your nth root of a divided by b. Here is that nth root of a divided by b. So when we are simplifying radicals using the quotient rule, we have to have another rule. And folks, I thought about this as I was getting this board ready. Some of you would be saying right now, I can bet on it. How many rules, Johnson, are there? Well, we've just about reached the end, so to speak. There will be actually one more unique one that we'll be dealing with. So we go to rule number 5. And rule number 5 is the rule that helps us simplify a radical using the quotient rule. A basic declarative sentence. No radicand can have a fraction. No radicand can contain a fraction. You see in this form, just right here? Look at your radicand. It contains a numerator over a denominator. It contains a fraction. You can't have a fraction as a radicand. So what do we have to do with him so we're not breaking that rule? We have to split him up. The nth root of the radical of a divided by b is equal to the nth root of a divided by the nth root of b. And that's what we're going to have to do in order to simplify when we see a fraction in the radicand. Now, I'm not forgetting this statement down here. I thought I would include it. Just because you can't have a fraction in a radicand, it does not mean that you can't work with that fraction for a bit to maybe get it simplified to lower values. So as a first step, when you're looking at the form of a radical expression where you have a fraction in the radicand, always check to see possibly if that fraction can be simplified. In other words, can the fraction that you're looking at, can it maybe be reduced? Can the fraction actually be divided if the numerator is larger than the denominator? Check to see if the radicand if that fraction can be simplified first. So let's go to number 1. We're doing square root. The radical of 5 over 144. Well, now 5 over 144 cannot be reduced. 5 is prime, and there is no 5 in 144. So it can't be simplified. So now we've got that out of the way. Now we're going to have to use the quotient rule of radicals to bust him up, to split him up. Why? Because the radicand cannot contain a fraction. So we're going to take this and we're going to split it up in this form. Let's put it right here. The radical of 5 divided by the radical of 144. Split it up. Now I'm not breaking rule number 5 because I no longer have a fraction as a radicand. I split it up. So now we look at this and we see if we can simplify it. The radical of 5 we can't do anything with. The radical of 144, folks, I believe that is rule number 1. I believe 144 is a perfect square, and I know that you know that it is. So he's going to come out of his house, and our answer is going to be the... Okay, we got cut off just a little bit right at the end of this problem number 1, where I said we can't do anything with the radical of 5, but you and I both know that the radical of 144 represents a rational. And this little piece, I think, got cut off of that last little video. Your answer is the radical of 5 over 12. And it has then been simplified. So we can't have a fraction in the radicand, and we didn't allow that to happen. We split it up using the quotient rule of radicals. He remained because he was already in simplified radical form. He was not. He became 12, the answer. All right. I've erased a lot of this stuff that had been formally up there. Let's go to number 2. We want to simplify this. The first thing, folks, that you want to do is look at the fraction. See if the fraction can be simplified. Because if it can be, then we ought to take the opportunity to reduce, to make things smaller. We can't do anything with 6 over 25. But we have one factor of x in the numerator, and we have 3 factors of x in the denominator. Let me just note this below this x to the 3rd right here, so there's no confusion. That x to the 3rd for just a moment is this. And we can cancel out the factor of x in the numerator with one of those factors of x in the denominator. They'll go. And we're now left with this. 6 over 25x squared. Again, there's nothing wrong with tinkering with the fraction for a bit. But now this has been reduced. Now we can't have a fraction in the radicand. So we're going to have to split it up. So we write it as the radical of 6 over the radical of 25x squared. We can't do anything with the radical of 6. It does not contain any perfect square factors. So it's just going to remain the same. The bottom, I believe he represents a rational number. 25, perfect square. X squared, perfect square. Its root, 5. Out of the house. Its root, x. Done. Done. We don't have a radical in the denominator. We're not breaking that rule. We don't have any fractions in a radicand. So we simplified. Let's go to number 3. The radical 360 over 10. Can't have a fraction in the radicand. But before we think about splitting it up, see if that can be simplified, that fraction. It can. We can knock off a 0. Or we can literally divide 360 by 10. They cancel. 36 divided by 1 is 36. And on this particular one, people, we don't even have to use the quotient rule because the entire fraction got eliminated down to a 36. It's 6, and it's done. Maybe what was the key item about that one? Well, we were able to reduce, simplify it. All right, let's pick it up and let's go to number 4. Staying with square root. The radical of 12 over r to the 12th. Basic. Look at the overall fraction. Can't reduce anything. You don't have any r's in the numerator. And you don't have any factors of 12 in the denominator. So we're going to have to split it up. That will now become the radical of 12 divided by the radical of r to the 12th. Well, it doesn't take much to look at that denominator and see that that radicand is a perfect square because its exponent is even and 12 is evenly divisible by 2. So he's going to come out of his house. The numerator of the radical of 12, he isn't a perfect square, but 12 contains a perfect square factor. You can prime factor. I'll just kind of prime factor this 12 up here just a ways, just so there's no doubt. There's our 2 of a kind. That becomes 4. So let's carefully do this. We need to use the product rule of radicals to split up that radical of 12 into the radical of 4 times the radical of 3. The bottom, he's going to come out of his house right away. 12 divided by 2, the square root of r to the 12th is r to the 6th. Come down. He's coming out. We'll get 2 root 3 over r to the 6th. Done. And it's been simplified. I think a word to the wise in working with this: don't try to skip steps. Don't try to skip any steps. You're going to lose. You're going to make mistakes. Be thorough. Show your work and show all of the steps, even those that you might think in your mind are not necessary to write down. They're necessary, I believe. Number 5, we'll change the index. The cubed root of z to the 5th over 64. Look inside the house. See if there's any reducing, any dividing, reducing. There isn't any. So we'll split it. That will become now the cubed root of z to the 5th over the cubed root of 64. Folks, if you already know that the cubed root of 64 is 4, then you don't have to worry about prime factoring that. But again, I've got a feeling that there's some people that are listening to me that would not look at 64 right away and see that its cubed root would be 4. Okay, so we're going to show some things. Let's take it one step at a time, and let's start with the numerator. Z to the 5th has an exponent that is larger than the index. So that means that within Z to the 5th, there is a Z to the 3rd. And we need to pull a Z to the 3rd out. Z to the 5th, 5 isn't divisible by 3. 4 isn't divisible by 3, but 3 is. So we're going to use the product rule of radicals and split. In the rational house, Z cubed. And in the irrational house, 5 minus 3, Z squared. You see, the product rule will get this back to Z to the 5th, so we've done it right. Now let's go to this one right here. 64. That's 2, 32. That's 2, 16. That's 2, 8. That's 2, 4. And that's 2, 2. Here's 3 of a kind. And here's 3 of a kind. So because that's a perfect cube, and that little collection is a perfect cube, we can unite all of these factors together by adding those exponents up. 2, 2, 2, 2, 2, 2 to the 6th. So now we'll get it to this. And now let's come down. The cubed root of Z cubed, Z. 3 divided by 3 is 1, so Z multiplied by the cubed root of Z squared. The bottom, bring down that 2 and take its exponent and divide it by its index. 6 divided by 3 is 2. And we'll then have Z multiplied by the cubed root of Z squared over 4. You always want to check this factor right here to see if it has any commonality with him. And they don't. And we're done. So you got to slow down. I have to slow down. I make mistakes. So will you. We're human. Right? Let's go to 6. It's a different little form. Back to square root, but looks like this. Rule number 2. If a radical expression represents a product of radicals, multiply them together to get a single radical. No, I wouldn't split this up. No, I wouldn't split him up. I'd multiply them together. Tells you to. So let's multiply them together. 2 times 1. 3 times 27. Now it's a prettier picture. Now, this can't be reduced, so we'll bust it up. The radical of 2 divided by the radical of 81. The radical of 2 stays the radical of 2. You can't do anything with it, but this is rule number 1 because he represents a rational of 9, and he's done. So multiply those together first. It's rule 2. Then you get it down to the radical of 2 over 81, where you have a fraction in the radicand, and you can't have that, so we have to split it up. One last one in this section, and it'll put a close then to... Okay, we'll finalize this 9.2 now by taking care of number 7. the cubed root of negative 54 over 2. Can't have a fraction, but once again, that fraction can be simplified. 54 is evenly divisible by 2. Don't forget the negative. And the negative sign is definitely okay, because remember, if the index is odd, the radicand can be any real number, positive or negative. And I believe we know that 27 is a perfect cube, so I'm going to show the upside. It's not lengthy. 3, 9, 3, 3. And now when we rewrite this, we'll actually have the cubed root of negative 3 to the third. Because negative 3 times negative 3 times negative 3 is negative 27. This is a perfect cube, as we can clearly see. Bring down that base. 3 divided by 3 is 1, so it just is negative 3 as the given answer. And that's it. And so that'll kind of now put a close to 9.2. And we'll reunite, okay, and move forward.